This one is this one evaluation? Wait, I can see.
I think it's weakening first.
It's weakening first, right? Yes. And then it is, so this one is weakening F away, right? And then we still have to derive this guy, right? And this one is weakening G away, and then we still have to derive this guy. And how are we going to derive this guy? Well, we're going to push F out of the context, right? I'm gonna look at my notes so that I don't mess it up. Like that. Wrong notes. So the point of this exercise is this is really not that easy. Yeah? And I'm loving that it's not that easy for you either, because then I'm going to show you how the proof assistant does all of this for you, and then you're going to be like, ah, now it's really an assistant. Okay. Give me a sec. If you're wondering what I'm doing, I'm actually looking into the textbook now. So my notes are the textbook. Almost done. There we go. Ah. Now I remember it. We have to do that. The actual evaluation rule. Right, so if I have gamma and f of type from A to B and x of type A and then f of x is of type B, then I can do the evaluation rule and get gamma f from A to B will get f from A to B. Okay, do you believe me that this is the correct evaluation rule? I don't believe myself. Let's check. So here, if I have this, then the upstairs thing is actually, if I have f of x and x here, I can remove this x, and I can remove this x and get f in the conclusion. And now this is just the generic element. It's just the variable rule, right? So all I have to have here is that in gamma, A arrow B is a type. And I'm done. Okay? And the other one is exactly the same, just to swap the name of the function f to the name of the function g. So here is the same thing, right? Here I have g and y. I do the evaluation rule. I get g on both sides, like here I have f, and then I'm done. Okay, so this wasn't easy. Very good. Very good. This is playing very well with what I plan to do next. Okay. We can derive in a similar fashion two more stuff about the composition. One is that it's associative. The other is that it satisfies the left and right unit laws. So the unit for composition is the identity function we derived right here. And then we can play with this. I don't want to do this by hand because this already didn't go well, right? And I had a cheat sheet. I could do it in principle. I think the full derivation of this is in the textbook, but I will let the rock do it for me, and I will let it assist me. So yes, like I said, the point of this exercise was we don't want to do this by hand, but if we have to, now we understand how to do it by hand. Okay, question? No, perfect. Next one, natural numbers. Okay? So we have the following rule for the natural numbers. The formation rule, shouldn't surprise you. The introduction rule, shouldn't surprise you. Here in the parentheses, I'm actually saying it's going to be the zero and the successor that I was already using in my examples. The elimination rule will be the induction principle, and then we'll have the computation rules that kind of tell you how these induction principles behave on 0 and the successor. And then we also, of course, have the congruence rules, but I will not do them because they're easy and it's always the same thing. If I have a symbol and I apply it to judgmentally equal stuff, I get judgmentally equal stuff. That's the whole story of the congruence rules. Okay, so let's look at the natural numbers. So the formation rule is easy. We just say n is a type. Good, I gave myself a type. Introduction rules are, slightly but not much more interesting. So I'm giving myself a 0 element, so an element called 0. That is a natural number, and I'm giving myself the successor function that says, if you give me a natural number, I'll give you the next natural number. Right? And so far so good. This is how we inductively define. But we have to give it the induction principle for it to mean the correct thing. Right now I just gave myself a constant that is a function from n to n. This could be anything in principle, any further rules. One more comment maybe. I'm here annotating zeros with little n, because in principle you could also call the integer 0 a 0, and the integers are completely different from natural numbers. Right? It's a completely different type. You could, help yourself with natural numbers to define them, but they're not the same thing. So it's nice if, like, every symbol, when you define a type, you should have like unique names for the symbols. Okay, it's very important that the constructors are unique for whatever you're doing. Okay. Elimination rule. So this is the induction principle in its nicest form, and the nicest is meant a bit sarcastically. So how does induction work on natural numbers? Okay, before you saw this rule anyway, right? How do you prove stuff by induction on natural numbers?
Prove that it's true for 0, and then prove that it's true for something, it's true for its successor.
Yes. So I will just repeat in the microphone. Prove that something is true for 0, and then prove that if I have a proof that something is true for some natural number, it's also true for the successor. And we claim that if I do these two things, we will have a proof for all natural numbers, right? So this is, a syntactic form of that. So the thing that we're proving, right, is the type family P here, okay? So it's kind of going with this propositions as types idea, right? Because what we are proving is kind of a proposition, so now it has to be a type, but it's a dependent type because it depends on which natural number we give it. Okay? And then we give ourselves a proof of 0, so this is this element P0 of, type P of 0. And then I'm giving myself this P successor, right? PS, and this one is actually a function with two arguments. One is the natural number. So give me a natural number, give me a proof that whatever P is holds at this natural number, and I'll give you a proof that the successor one is also true. And the conclusion is that if I have all of these three premises, then I have a term of type for all natural numbers P of those. For all natural numbers n, P of n, right? So this is the conclusion. I'm saying it holds for all natural numbers, which means I'm giving you a function that you give me a natural number, so I give you the proof. So I'm introducing this new symbol, int n, right? And this is, the symbol corresponding to the induction principles. We always have symbols. We had a new symbol lambda, we have the new symbol EV, we have a new symbol 0, and every one of these elimination rules also has a symbol. It's called the induction symbol, right? Induction on natural numbers. Maybe before we go a little bit further, I want to comment on what is the correspondence between these derivation trees that we're doing and the proofs that are, terms, propositions as types thing. Because if I ask you what's a proof, and you've heard me talk for 2 hours already, how do you answer that? What do you think is a proof? A term of a type? Yeah. But if I write gibberish of a type gibberish, is that also a proof, right? So it's not just a term of a type, it's a well-formed derivable judgment that certain term has a certain type, right? So for example, if I want to have here, if I look at just the second line, right, if I say P0 of type P0n, I would want to derive this judgment to say P0 is actually a proof of this term, and the derivation are these derivation trees that we just did, right? I cannot just write, I cannot just, say Anja colon P of 0n, because Anja doesn't have a sense in my type theory, right? I don't exist within the type theory, I exist outside of the type theory. And, I'm playing God and, manipulating it and having fun, and look, it works, or oh no, it doesn't. Oops. And here, P0 actually has to be something that works, right? So, of course, here it's written in a hypothetical form, but if you want to have a full derivation of a full proof, right, you have to have not just a proof, a well-formed term, like syntactically, right, but it also has to have a derivation in this sense that we're doing, right? So we can derive using these terms, these rules, these inference rules that we're saying now. And actually, when you're doing proving with a proof assistant, right, every time when you're constructing terms, right, you're already using all of these derivation rules on the go, right? So what you're constructing in the end are only well-formed stuff. Otherwise, hopefully, otherwise the proof assistant won't accept it. Right? That's the dream. It's not always the case, but that's the dream. Okay. So let's look at this induction principle, and let's add the computation rules, right? I said these P0 and PS should kind of say what it's meant to happen on the 0 and the successor. So when you apply this induction to 0, so here you see I can give it another argument, the n, the natural number, and if this argument is 0, then it should be just judgmentally equal to P0. And if I'm giving it a successor, right, it has to be judgmentally equal to this PS applied to the proof of the previous guy, right? So it's PS applied to the previous natural number, so this is a successor, then the previous one is n, and the proof of the previous one, right? This is what it has to be judgmentally equal. Because remember, this guy says, give me a number, give me a proof that equals for that number, and I'll give you the successor, right? So you have to give it a proof of the previous one, right? Previous judgment. Okay. So let's try to use this induction principle like in practice. And I'm going to make you suffer a little bit, trying to do this by hand, so then you will again appreciate when the proof assistant is doing the heavy lifting for you. Okay, so how do we define addition using this induction principle? So morally, what do we want? We want to define a function called add that takes two natural numbers, so it takes a natural number and then takes another natural number and gives you a natural number. And addition works such that if I'm adding 0, I'm doing nothing. So m and 0, if I'm adding m plus 0 is judgmentally equal to m. And if I am adding a successor, then this is just like successor of the addition of the previous two. So I decided to do this by pattern matching of the second argument, right? You could also say it's induction of the second argument. I could easily choose the first one. It doesn't matter, but for the sake of choosing one, I chose the second. So this is what we morally want to do. And now let's formally derive it using this induction symbol, okay? So formally what we want to do is we want to derive this function, and because it's induction of the second argument, right, the first argument m is fixed, it's in the context, right? So our induction rule that is being used, our gamma already has variable m in the context, and I want to define add of m to be here, look, it's a function from natural numbers to natural numbers. So usually when you think of addition, you think of it, okay, I'm applying it to two arguments and getting a natural number. But because we're doing it with the induction principle, we're actually getting a function that is dependent on the second argument, right? And it's going to be this ind symbol to applied to, something, this P0 will be this add 0, and PS will be this add suck, right? And we have to define these two guys, okay? And they have to hold, certain equalities have to hold for these two add 0 and add suck, and the computation rules will tell us which equalities they have to hold. So, right, add 0 has to be of type n. So yeah, first of all, when we look at what our type family is here, right, I'm saying, okay, what is my goal? And here, my goal is to get a just natural number, right? Addition will be just defined as one natural number that is the addition of two numbers, okay? So I know now that my P of n is just the type of natural numbers, and then the add 0 will be, well, of type P of 0, which is again the natural numbers because there is no dependency. And this one is also just the natural numbers, and this one is also just the natural numbers. So actually, the type of add suck is from natural numbers to natural numbers to natural numbers. So I, obfuscated some of the dependency because it's a simple enough example. Question?
I have a question about the rule for the rule on the previous slide. Maybe I'm missing something, but why in the successive rule shouldn't we be allowed to assume that n is non-zero?
Here you want to say that n is non-zero?
Yes. Or no?
No,
Maybe
no.
that doesn't
No.
make sense.
Because then you don't have anything for 1. So if I give you n is 0, and you give me a proof of P0, I'm giving you a
I see.
proof at 1.
I see.
Yes.
Thanks.
Is this induction or strong induction?
I don't know the difference between induction and strong induction.
Or
So
induction is just assume that we prove n plus 1, and then strong induction is like we assume from 1 all the way to n, and then we prove n plus 1.
okay. So whether it was in just the previous step or all of the previous
Yeah,
steps.
yeah.
So I think here we're just assuming the previous step. So if I'm giving you, so this PS works that I'm giving you a number. If you give me proof just for that number, I'm giving you the proof of success.
Okay.
Right here, I don't have proof of all of the previous numbers.
Is there another set of rules for strong induction or no?
I don't know, but I don't think it's
You
true.
can always,
It's
you can
always-
always write strong induction.
Yeah.
Yes.
Yeah. Okay.
Okay.
Sorry, can I ask about, for the successor constructor, is this somehow distinguished to be injective? Like, how do we know that the successor 0 is not equal to 0?
We don't. At this point yet, we don't.
Okay.
Yes. So the fact that 0 and 1 are different, right? We can prove that, but we need some knowledge of the universes.
Okay.
So, chapter 7 in the book. Section 7.
Thanks.
So far we don't yet, but I mean, we can prove that in Martin-Löf type theory, but not with just the rules I showed you at this point. Yeah. Okay. Where was I? Yeah. And then add suck has to have this type, and now, okay, we can define add 0 of m to be just the m, because adding 0 does nothing, it's an identity function, so we know that add 0 will just be m. But what we want to do for add suck, right? Well, we know that this equation should hold, right? So if I'm applying add this induction to suck, right, then it should be the successor of the previous one. Well, yeah, the previous proof, so to say, right, previous number. So actually what we want is that add suck, if you apply it to m, n, and the previous result, it's just the successor of the previous result. And this suck of x, where x is the previous thing, is derived by looking at this, because this here is the previous guy. So that's why we do x here. And we can check, right, that if we define this add suck in this manner, and we now compute from the left-hand side that we really get this, right, so m and suck n, it should be the induction of add 0, add suck, and then suck n, which computational, like computation rule 2, will be mn and the previous guy, and because @suc will just take the successor of the previous guy, it is just the successor of the previous guy. So we see that this and this gives us exactly the correct equation that should hold. Question?
So, sorry, I'm a bit lost on what we're trying to do here. What I understood so far is that we have a reference definition, which is the one above, and then this @0 @suc-based definition, which is a forward, and we're trying to prove that the forward sort of coincides with the definition on top.
Yes.
Okay.
So this definition on top is our reference, what we want to do. Now we're formally defining, so it's not really, it is a derivation of this definition, right? But we are defining m to be the induction on this guy, and now we want to make sure that whatever we defined here in this line, so this is my definition here, see int n @0 @suc, right? And these @0 @suc are defined in this way, such that this, whatever I get here, is the thing that I wanted in the first place. And what I wanted in the first place is presented here by pattern matching.
Thank you.
Question?
I'm definitely reading these problems and not understand how @suc just takes one argument there, but it's taking the arguments at the bottom.
Okay, where is it taking just one argument?
We've got @suc and there, are we just saying that @suc is dependent on m? And we're not?
@suc is dependent on m, yes. And then @suc when it's dependent, so for every m here, I will get a different @suc here.
Okay.
Yeah? And when I'm fixing my m, @suc will be a function that takes two other arguments, n and x,
Oh.
here. And it takes two other arguments because the induction principle is designed here to take two other arguments. You see, here's one pi and one arrow. So these are the two extra arguments. Pretty sure you're not the only one who was confused by that, so thank you. Okay. More questions about this? No. Perfect. Now, formally, right, because we want to say that whatever we define is well formed, we have that @suc is lambda n suc n, because this is how we defined it, right? And then we have to make the entire derivation, and then we have to make the entire derivation of the entire induction thing, and and it's getting kind of wordy, right? So we did this now formally. We have a big derivation here. But I want to tell you that actually pattern matching, the thing that was our orientation, is first of all more readable than this thing, and second of all, it's sufficient for proof assistance. So this whole derivation thing that we were doing now is another painful exercise that you did once and for all, and from now on you can just use the thing that we're already used to, which is the pattern matching thing. And also, when you do it in rock, for example, you will define stuff with pattern matching or with, the induction keyword. Yes.
Okay, you having said that, maybe this is a bit of a redundant question, but I guess if you don't mind clicking so that the other steps were present below on the slide that's showing, yeah. So basically this is saying, if we're wanting to show a proof of 5, we're going to have a specific @suc function that is dependent on 5 that we're trying to prove, which ultimately is the same as if we were trying to prove 4. But because because the dependency is on 5, we're kind of collapsing some of that dependency because we're saying it's judgmentally equal to successor of n generally.
So you mean that this is just suc x?
I think so.
So I'm not really sure what you're saying, because depending on what m and n are, x is a different number.
Got it. Okay.
Yeah.
Okay. That makes sense. Thank you.
But ultimately you will get the right thing if you just, substitute m for whatever number you want in the context, right? But it will be a different number depending on what m and n are. It's the sort of the previous thing, right? That's the idea.
When you said that pattern matching is sufficient for proof assistance, does that mean that like pattern matching desugars into a proof like this, or they have some other way of implementing this type of logic?
Mm-hmm. This is exactly what happens. Pattern matching will exactly desugar into this thing, and if you print the term, it can give you the int n and all of the blah 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 thing that then, and sometimes you will, most of you already know calc or lean or whatever. So when you say you derive something using the tactics and then you want to see the term that you have, I usually don't know how to read that anymore, especially if it's a long proof, right? But at least I recognize some of the things. And if I did induction at some point, there will be an int term former somewhere in there when you print it. So yes, it just desugars into this. Yeah. More questions? There was somewhere here. Yeah.
I think I got lost again at some point. That the area of add sub m looks like it takes 2 arguments.
Yes.
And the area at the bottom looks like it's taking 3 arguments. Is that because of the currying with the m?
Yes.
Oh, okay.
Yes. I just wrote it shortly. You could say add sub of m, and then it's of n, and then of x. But I just curried it. Yeah. More questions?
Here, I have a question.
Yeah.
Just going back to the pattern matching thing, desugaring to induction and whatever. If like in lean especially, pattern matching reduce or desugars into like a recursor, which is a thing like similar to induction, right? Is the recursor always a non-dependent version of induction?
So recursing meaning a match?
Yeah, no, like there's from what other textbooks I've read, it's like there's an induction principle for stuff, but there's also a recursor.
Mm-hmm.
Yeah, and it looks identical. And like lean desugars pattern matches used into recursors. Yeah, so what's the relationship between like recursors and the induction principle? Is it always the non-dependent version, or?
So my question for you is, because I'm not entirely sure,
Okay.
you mean by the recursor that it doesn't take the previous proof?
No, like the result is not dependent on like m, n, or x. The type, I mean. Like type is just a natural number.
Type of what is not dependent?
Like the result is just n, it's just a natural number, right?
Okay.
It's not dependent on m, n, or x, right? Yeah.
Okay.
So I think that's the recursor.
Okay. So
Yeah.
it's simplified. It's a non-dependent version then.
Yeah. Oh, okay.
So
Cool.
this is stronger.
Right. Okay. Cool. Thanks.
Okay. Let's move on. So yes, pattern matching is the way to go in practice, but if you have to go into the int world, now you know where it comes from. Okay. We have more inductive types in the Markov type theory. We have the unit type, because if you remember the Curry-Howard, it's going to be the truth. And it only has one constructor. I will write it with a star, okay? And there is an induction principle, but, look it up in the textbook. It's not very interesting. A slightly more interesting one is the empty type. So the empty type is sort of like the false proposition. And the empty type has no introduction principles, introduction rules, no constructors, it's empty, right? But it has an induction principle, okay? It doesn't have a constructor, it has an eliminator, right? It doesn't have an introduction rule, it has an elimination rule. And the induction principle says that, give me a term of the empty type, and then you can basically prove anything you want, right? And the non-dependent version is, the so-called ex falso, which is the induction principle where the type is just non-dependent, and it's a special case. And this is the one that we usually do. So this basically says, from the empty type you can prove anything, right? If you give me an element of the empty type, you can prove anything. Interesting interestingly enough, and I slightly regret I didn't include that one on the slide, is that we can also define negation as, so if I have the negation of A is the type of A arrow empty. Okay. So if we prove a negation, we say, give me an element of A. If I have an element of A, then I have proof of false, so I reach a contradiction, right? So just probably preaching to the choir here, but the proof of negation looks like assume A, give me a contradiction, I have a proof of negation. This is not a proof by contradiction. Okay? The proof by contradiction is saying, give me a negation, and then derive a contradiction, and then A holds. Okay? And these two are constructively, which is what we're doing, not interderivable, and this is because this double negation rule is just not true. Okay? So not A is not equal in any sense to A in general. So I'm just saying, so in certain cases it is true, but not for every type A, double negation is equal to, it's that this is not true in this setting. So I'm just saying that if we derive a contradiction, it doesn't mean it's proof by contradiction, it just be a proof of negation, and this is okay, this is allowed. This is nice. Okay. We have co-products, which Brigitte already did, and I will not do because they're the same. So there is no dependency there. I will talk a little bit about the dependent sum, or dependent pair. And the last one, and this one will probably be for tomorrow, is the propositional equality. Okay? And once we have those, we can do the full query Howard. Okay. So the dependent sum, I'm not going to give you the rules here, I'm just going to cheat a little bit and give you the syntax, and then you can read and reimagine the rules. So dependent sums are in a way similar to dependent functions, and it is that it's actually a proper dependent type. Okay? So we write them with a sigma. Kind of looks, if I wrote pi here, it would look like the same as dependent functions, but now it's a sigma. And what it does, it's a dependent pair, okay? So it's a pair of two stuff where the type of the second component is dependent on what is in the first component, okay? Before we had a function where the codomain, depends on the argument. Now we have a pair where the second component depends on what you threw into the first component.